Hello, Honors Chem students. This is Mr. Keister here with you again. This is the video for Tuesday, September 8th, 2020, which is our first day back after the Labor Day holiday weekend. This is our scheduled 13th day of school for the fall semester. Always remember, though, that the dates could change for a variety of reasons, but the lessons, regardless of that, will remain in the same order. So let's look at today's do nows, our schedule for today. Today we're going to start, at least collect the data for and get rolling on lab activity 1-2, part A, which involves mass, volume, and density. Friday, of course, we had our exam, and you took it from home during our e-learning day. Hopefully that went well for you. We're today going to be collecting mass and volume data for both copper and zinc. And we're going to record that data on an Excel spreadsheet that I have on my computer. And then we'll compile the data, and I'll put up the resulting Excel graph on the front board that you'll want to take a picture of and use to continue on in completing this discovery. I'm also asked that on the back of your paper that you sketch a graph on the back of the handout of the class data graph with all the other information that I have on the front board, which is actually right here. So anyway, homework for tomorrow. Once our Excel graphing is completed and posted on the board, then you are to answer, we're going to go through questions 1 through 4, and then you are to answer questions 5 through 11 for tomorrow. I've also assigned our next mastering. You had a mastering due today, by the way, 1-1A. Our next mastering, 1-1B measurement, is due this coming Friday by 7:30 a.m. All right, so 1-1B measurement is due this coming Friday at 7:30 a.m., and I have opened it for you. So let's look then at our lab activity today. So again, this is 1-2A, which deals with density, mass, volume, and density. So now that we have the tools and the knowledge to measure correctly the size or volume and the amount or mass of a substance, it would be useful to see what relationship exists between those two. In this activity, you'll measure the mass and volume of samples of two metals, metal A, which is copper, and metal B, which is zinc. Then we're going to graph the data and examine the relationship that exists between mass and volume. So we are going to head back to the lab, and I'm going to record all 6 masses and volumes for the samples of copper and zinc. Notice we also have a 7th piece of data, which is 0, 0. All right, for both. Think about that for a second. If we're graphing mass versus volume, is 0, 0 a valid point on the graph? And I would hope that you would say that yes, it is. Because if we have no particles of a substance, then of course they don't have any mass, because mass is dependent on quantity of matter. So if we don't have any, then mass would be 0. And if we don't have any particles or quantity of matter, that it takes up no space either. So no particles, no mass, no volume. So 0, 0 is a valid point on any mass versus volume graph. Okay, so let's head back to the lab and we will collect the data. It's up here, and we'll head back here. Oops, I forgot my lab paper. Good one. We'll just take the long way back. All right. Let me set this up here where hopefully you can see me. And the data we're collecting, probably need to switch it down a little bit. And let's see, we got my, you can see I've got my electronic balance here. And over here we have got, we're going to need a a graduated cylinder and some water. And then I've got the 6 samples of both copper and zinc in these cups right here. So let's see. Here we go. Oh, that seems reasonably good there. All right. So for what I'm going to do is the masses first, and then we'll do the volumes second. And the reason I want to do that is you can see here some of our samples, if you look in there, some of our samples are small pieces. And so I can't, or like this one, they are irregularly shaped larger pieces. Either way, with an irregular shape, remember we are not able to measure volume directly with a ruler, and so thus we would have to find those volumes by water displacement. So of course that'll get the pieces wet. So I think it would be wise if we do all the masses first, and then we'll come back to the volumes. So let's run through the copper first. So since we're doing some of these are pieces, I'm going to put a container here so the pieces don't go everywhere. So I'll zero out the balance there after there we go. All right, so copper sample 1. So we're on line 1, mass of copper. I'll pour those in there. And it says 20.12 grams, 20.12. Put those back in there. Now, copper sample 2 is actually a regular solid. So think about that when we do volume. I'll go ahead and put that right there. And the mass is 142.08 grams. So that's mass of copper for number 2, 142.08. Number 3 is cylindrical. You think, well, heck, what did I say that for? I meant to say hello. All right, so oops, faux pas there. Meant to say hello. Anyway, you're thinking, well, now this is a cylinder, so could we not find the volume of that sample directly? And the answer is no, because if you look at the top there, there's a little like a handle type piece on there, which would mess that up. So we're going to have to do volume on this one by water displacement too. If it wasn't for that little thing there, we could do it. Anyway, number 3, mass is 54.87 grams, 54.87. Number 4, again, we got pieces here, and that is 9.83 grams, 9.83. Put that back. And number 5, got a rectangular solid here. Number 5 is 63.05 grams, 63.05. And the last sample of copper, number 6, we've got a lot of pieces in that one. There you go. 64.96. 64.96 grams. So get all these pieces back in the cup here without spilling them all over the place. Come on, I got one straggler there. You don't want out of there. There we go. Okay. So that takes care of the masses of our copper samples 1 through 6. Let's now do the zinc ones. So here's zinc sample number 1. Its mass is 31.88 grams. So that's the mass of zinc number 1. Okay. Zinc number 2 is a bunch of little pieces here. No, actually not little pieces. They're somewhat large. 32.31 grams. 32.31. Zinc number 3, got some bars again, irregularly shaped though. 34.61 grams for number 3 for zinc. 34.61. Number 4, we've got, again, these oddball shaped pieces. Again, I don't know if you can see them. There they are. And there's that. 39.16 grams for that sample. And zinc number 5, back to these oddball shaped little bar looking things. Number 5, 32.92 grams, 32.92. And our last one, number 6, again, got some bars again, 38.39 grams, 38.39. So we have the masses now for all of our samples. So now we'll go back and do volumes. All right. So we'll go back to copper now. So volume 1. Now with these little pieces, we're going to have to do water displacement. Make sure I get an ample amount of water in there. All right. So looks like we got about 50, right on the line, about 15.0 grams, or 15.0 mLs, excuse me. So let me put the copper in there. And it has gone up to 17.2. So that would give us a volume then of 2.2 mLs. Remember, with these graduated cylinders, the value of the smallest marking is the ones place, and so we would have to go to the tenths. So 2.2 mLs for sample 1 of copper. Pour the water out there. Put my copper here on the paper top. All right. Number 2. Okay, so copper number 2 is actually a rectangular solid. We can find its volume directly. So let me grab a ruler over here. There they are. And it looks like about 2. I'm going to grab my calculator. I'm going to have to calculate volume. Length, width, and height. Of course, it's a cube, so length, width, and height are all the same. Looks like we got about 2 point, it's right in between 0.4 and 0.5. So I'm going to say somewhere around 2.45, it looks like. I'm going to multiply that out. Actually, it looks closer to 2.50 now that I look at it again. Had to slide that over to hit the 0 line. Let me do a quick length times width times height again. Puts this right close to around 16.0. Of course, we're going to have to, since I rounded to 2 decimal places, it gives me 3 sig figs. And when you're multiplying, of course, we round to 3. So based on this, let's put 16.0 centimeters cubed for its volume. Centimeters times centimeters times centimeters, centimeters cubed. Keeping in mind, though, later on that a centimeter cubed and an ml are equal volumes. We talked about that back in a previous lab activity where you graphed centimeters cubed versus mLs, and we found the slope of that line was right around 1. So actually a cube that is 1 centimeter on a side will hold exactly 1 ml of liquid. So centimeter cubed, ml, same volume. Okay. All right. Number 3 is this cylindrical shaped thing, but it's got that little thing on top, so we're going to have to use water displacement again. Okay, looks like we got right about 10.0 mL, so I would say, yep, I'll slide this in nice and easy so it doesn't spill any water out. And it looks like it raised up We're at about a little over 16, so about 16.1 minus 10, 6.1 ml, 6.1. So that would be our volume for number 3, 6.1 mLs. Number 4 is little pieces again. So I need some. There we go. So we'll put those in there. And let's see. Well, that didn't go up much. Looks like it went up by about 1.0 mLs. Close as I can tell. About 1.0 mLs for number 4. Again, we're on copper. Get little pieces out of there. Okay. All right. Number 5 is a rectangular solid, so we can find its volume directly by measurement. So let's see, looks like about 4.30 on one side, on the long side, and about 1.20, 1.15, somewhere in there. And the other side is about the same. 1.20 looks like. Measure that again. Okay. And that puts us at a volume, according to my calculations, of right at, and again, this would be to 3 sig figs because all my measurements have 3 sig figs since I went to 2 decimal places. 6.16 centimeters cubed. 6.16 centimeters cubed for number 5. Again, it may make understanding that that is also equivalent to 6.16 ml. So either way. All right, so we'll put that one back. And then we'll go to our last one, which again is going to require water. So we'll do water displacement. Okay. Got quite a few in here now. So it's like right about 10.0 again. So I'll put these in here. Got them all? Yep. All right. And that went up quite a bit. 18.2 maybe? Minus 10. 8.2. All right. 8.2 mLs for copper number 6 for volume. Okay. So that takes care of the coppers. Put those over here. All right. I'll be back with you in a second. Dealing with all these little pieces here. All right. Now we are to zinc. All right. So the zinc, looks like all the zincs I'm going to have to do water displacement. So we're doing a lot of this. So let's see. Okay. Here's the first one. Well, I thought easier just to drop them in there. Get them all submerged there. There we go. Looks to me like, let's see, let me do my little subtracting here. Looks like about 4.3 mLs. 4.3 mLs for zinc number 1. Zinc number 2, which is a bunch of little pieces. Get my initial volume there, about 19.0. All right, so put the zinc in there. Try not to spill them. There we go. And looks like that went up about right at 5. So 5.0 mLs for number 2, zinc, 5.0. Okay. Number 3, back to these bigger pieces again. Drop those in there. There we go. And after subtracting those, let's see, 3. Okay, looks like we're at about, I would say, right around 5.0 mLs again. 5.0. Which seems a bit odd, but yeah, that's what it says. All right. I guess it's not too different. 32.31 in number 2 was 5.0 mLs, and 34.61 is also 5.0 mLs. That seems reasonable within, limits of error. So now we're to number 4. Water back in there again. Make a mental note of that volume. Here's number 4. It's like we went up about 5.5 mLs. Yeah, about 5.5. And number 5. Really need that much water. There we go. Note the volume. Put these pieces in here. Again, want to make sure when you put those in there not to splash the water out. Okay, looks like that one went up about 5.2 mLs. 5.2. And last but not least, number 6. Make a mental note of that volume there. Here are the pieces for number 6. Slide those in there. Do a little mental subtraction there again. Looks like our volume is 6.5 mLs for number 6. 6.5. All right. Now, clean up my mess here a little bit. Calculator over there. Didn't get my lab paper too awfully wet, so. All right. All right, trying to pat dry my pieces here, so get them dry. All right, let's head back to the front. Okay. Right there. And we're back in business. There we go. That's good there. Okay. All right. So I'm going to put the data in the Excel program, the graphing program, and we're going to put that up on the board. So here is the data table. I know it's kind of hidden behind my writing here, but that you don't have to worry about that anyway. But I just wanted to tell you that I plugged in the mass and volume for each sample of copper here, 1 through 6, also including number 7, which was 0, 0. And then over here to the right of that, I did the same thing for zinc. Put in the points for mass and volume for the 6 samples. Again, 0.7 is 0, 0. And then when you plug that in and do the little Excel magic here, we get a graph right here. All right. And I have sketched that graph over to the side, so we'll look at that here in a second. But I wanted to show you that here in the orange color, nice, huh? Orange and blue. I didn't actually do that. It came up that way. So anyway, our orange data is for copper, and our blue data is for zinc. And so what you can see Excel did here, what we would have done if we graphed it manually, is draw a best fit line that incorporated as many of the points as possible, and the ones that it couldn't incorporate directly on the line, you try and have a not equal number, on either side of the line and kind of about the same distance, which takes a lot of subjectivity if you're graphing it manually. Excel, of course, has a brain far beyond me, and so it draws a much better line. So anyway, and what we have seen here also is it is also giving the slope-intercept equation for each line. And we will go over that over here on the board where I hand wrote it. It's a little bit bigger, you can see it better. But I just want you to see then that here is the line for copper, and here is the line for zinc, and you can see the slopes are different. Okay? All right, well, let me remove the graph here, and we'll go to the handwritten things over there. Let me just turn this a little bit this way so we can see that better. All right. Okay, so what I did was, using our sample data here, was hand draw the graph. And of course, I don't have graph paper up here, so like I said, it's not near as good a graph as the one on Excel, but it does the job. So I have mass over here on the y-axis in grams. I have volume on the x-axis in mLs or centimeters cubed. Remember, those are being the same. And I graphed each of the data points. Now, I did copper's data in black, and I did zinc's data in blue. Hopefully you can see that. Maybe I'll bring that even a little closer. Maybe that helps a little bit. So I have copper's data here, zinc's data here, and I drew a best fit line, to the best of my ability anyway, and utilized the slopes that the Excel data and graph provided us. So we will talk about those here shortly. So let's first talk about slope, all right? So slope, of course, is equal to rise over run, which is a change in y over x, over the change in x, which of course then is y2 minus y1, or x2 minus over x2 minus x1. Of course, you only need 2 points on the line to determine the slope of the line. For this particular graph, our slope is equal to the change in y, which is mass, over the change in x, which is volume. So for this particular graph, the slope of our lines are the change in mass over the change in volume. Well, the ratio of mass to volume is called density, all right? And so the density equation is right here, D equals M over V, ratio of mass to volume. And in fact, this is how the density equation was derived. It was derived directly from the graphical analysis of data, just like this. We're going to see that a lot in chemistry. We're going to end up using a lot of equations over the course of this year, but all those equations just didn't magically appear out of thin air. All right, all those equations were derived analyzing data, all right, and then coming up with the relationship between those data, such as here, the relationship of mass over volume, y over x, is equal to that substance's density. So I'm not just going to throw equations at you. say, oh, well, here's the equation for density, D equal M over B. Let's do some problems. I'm not going to do that because I would be failing you as a teacher in doing that. You know, D equals M over B is great. It's a great equation to use. But you need to know where that equation originated. Like I said, we just don't have a bunch of smart guys sitting in rooms, you know, deriving equations. These equations come from scientific analysis of data, and that's good science. Okay. So anyway, so using our sample data, and I wrote the equation here for the slope-intercept form, y equal mx plus b. Now you notice that I wrote b is 0 for a density graph. Why is that? Well, b is the y-intercept, right? And as we said, the y-intercept on a mass versus volume graph is always going to be 0 because, as we said before, 0, 0 is a valid point on a mass versus volume graph. Because, again, if there's no particles, then no matter, then no mass, no volume. Okay. So, for copper, our Excel said y is equal to 8.60x based on the data we took. So 8.60x plus 0 would be the full equation. Of course, since the y-intercept is 0, you don't need the plus 0 in there. So the slope of our line is 8.60, which then translate, as we said up here, to a density for copper of 8.60 grams per ml or grams per centimeter cube. For our zinc data, y was equal to 6.50x plus 0. So again, we don't need the plus 0. So the slope of our line is 6.50, which then gives us a density for zinc, based on our data, of 6.50 grams per ml or grams per centimeter cube. So why is the unit grams per ml? Well, the slope of this line, or the density, remember, is y over x. Y is in grams, x is in mLs or centimeters cubed, and thus the unit for density. Okay? Again, that unit comes straight off of data analysis. All right? So that basically takes care of graphing and explaining the relationship that exists between the ratio of mass to volume, which of course is density. So let's put this back to the main board here. And let's look at some of the equations here. So number 1 says, well, we checked our data, we did that. Number 2, we put our data on the Excel sheet, all right? Number 3, we looked at the Excel graph on the front board. And number 4, we sketched a graph over here. I asked you to do the same on the back of your lab activity paper. So again, you could take a picture of this data if you didn't get it all down as we were talking about it, and write it down on the back of your paper once you finish watching this video. So sketch your graph on the back of the paper. There's plenty of room on the bottom half of it. And based on the Excel graph that we showed on the front board, just like we did right over here. And then we're going to use the graph to answer questions 5 through 8. Now, I asked you on the schedule, on the do nows, for you to answer questions 5 through 11. We've already answered number 5, so we can go ahead and write that in. And so the slope for copper, which was 8.60, and again, grams per ml or grams per centimeter cubed, remember either one. And the slope of the zinc line was 6.50, again, grams per ml or grams per centimeter cubed. All right, so what I'm going to ask you to do then is to go ahead and answer, well, you know what, let's do 6 and 7, then I'll let you start with 8. How about that? All right. So what does the slope tell us about the two metals? Well, first thing it tells us is their densities aren't the same, all right? And we said that copper's Slope obviously is greater or steeper, and so let's just write that down. So copper's slope is greater or steeper than zinc's slope. Okay? It is greater. And remember that slope, the second question, what does slope represent in this activity? Remember we said that the slope of a mass versus volume graph is equivalent to density. Okay? And then finally, question 7. How does the density then of copper compare to the density of zinc? Well, based on the slopes, copper then is more dense than zinc. So I'm going to have you pick up with question 8. I do want to read it to you and have you think about it. In the boxes below, draw a particle diagram that compares a piece of copper and a piece of zinc, assuming the pieces are the same size, meaning they have equal volume. All right. So I drew the boxes here the same size, or tried to show that we have the same volume of each sample. So based on copper's density as compared to zinc's, remembering what density is, mass over volume, if the volumes of each of the two samples are the same, then how does that relate to the mass of each? And how would you express that in a particle diagram? So I will have you begin with that, and then I would like you to also answer questions 9, 10, 11. We will start tomorrow's day by looking at the answers to those questions, and then we will move on to lab activity 1, 2B. So that's it for today. This is Mr. Keister signing off. I hope everybody stays safe. Until next time, we'll talk to you soon. So long.